All right. So to start where I sort of ended last time, I want to understand the origin of, well, gravity and other forces, but I want to do it in a certain framework where I think about the phase space of our universe, and I'm going to make a picture of it. So by phase space, I really mean the microscopic phase space from which things should start. And so qualitatively, we want to think about the parameters that describe positions of particles and matter in our space-time as the phase space that we normally use. But that will be a subspace of a bigger phase space from which I'm going to derive the forces that live on this the smaller phase space. So we have a big phase space of fast variables. And here we have a small phase space and where we have slow variables like the variables x that I indicated as the positions of particles. Now, the idea is that the parameters that control these particles are basically derived from the bigger phase space, and they influence it, and then you can get reaction forces. I'm going to make this much more precise by looking at examples that we know in string theory, and also telling you more about what are the variables you should think about in describing this bigger phase space. And I'm going to put a name for it. I mean, I'm going to call this actually the Higgs branch. And this small phase space can be thought of as what's called the Coulomb branch. This is a language that's borrowed from string theory, but I think it will apply much more generally than just in the examples that we know about. My goal is sort of to, as I said, to understand gravity, and you would like to do this in a very generic fashion without specifying too much detail about what the microscopics may look like. So what I will do indeed is sort of eventually identify two important quantities in describing the big phase space. I'll do this in an analogy with what we know of conformal field theory. I'm going to introduce two numbers which I call basically C and N. C you can think about as the number of degrees of freedom. Sort of like what we do in conformal field theory, and call it the central charge. And N is more like the number of excitations, which is more like, say, L naught, like you have in a conformal field theory. You have also the number, the central charge, characterizing what's the number of degrees of freedom, and L naught is sort of telling you the quantization of what excitation level I'm at. So this is actually modeled, as I said, after things we know in
It's not characteristic of the theory
of the state.
C is characteristic of the theory.
Yes, but as you will, I will make clear. I'm going to associate a phase space with every region of space-time. So I'm going to think about a part of space-time, and then we're going to ask what is the phase space that I'm going to associate with that. And then C will be actually determined by geometric data, or actually there's a translation from what C is to the geometric data. And the same with N in terms of the energy of the content of this. So there will actually be eventually a way I express these formulas in terms of the energy in the system, the area of what's around it, and even the dimensions of the system.
That formulation doesn't have space.
So this will be translation then of these variables into the space language. So I'm gonna start from a big phase space, which then may have smaller parts in it, which I'm gonna associate then with parts of whatever the smaller phase space is that I have here. So I'm gonna actually think about space-time as really embedded in the bigger phase space, and it's gonna derive its geometry and its forces from how it's embedded in here. And there will be many more variables that are necessary to describe the entire thing than the one we normally use in space-time. And the
so far that's a classical picture.
This is why I call it phase space, but you can think about states, and I'll make it into.
Hilbert space.
You can think about Hilbert space, and
Hilbert space is isomorphic.
Now, okay, now you have to wait a minute, and then I'll describe an example. All right, there's a question, another question there.
Your space-time is embedded in a much bigger phase space, how can you call it inversion? To me it looks more like you just made your whole setup much bigger.
So eventually we have to define the parameters that, I mean, you start from a language in which space-time may not even be part of it, but you have to define what you call a coordinate eventually in terms of the original variables that I have. I'm going to give an example. Actually, let me actually go to the example, because this language of the Higgs branch and the Coulomb branch is borrowed from things we know from string theory. And I'm going to indeed look at situations where we know quite well what the microscopic phase space looks like, namely in terms of black holes. For black holes, we have the Bekenstein-Hawking entropy telling us how big the phase space should be, because there's a direct link between the entropy and the number of states, and therefore the volume of phase space. And if we then think about how we count states, we have precisely this kind of language. I'm going to do it in two situations. In two situations that we know quite well. They're sort of famous ones. One is the D1, D5 system. So that's the original one by Vava and Strominger. And the other one is going to be more an M-theory language. So this is actually what we do in 2B theory. And here people generally look at compactifications from 10 dimensions to 4 dimensions, or 5 dimensions actually. Like you take type 2B on K3 times S1. But there's another example which even gives 4-dimensional black holes. Here you start from M theory, or let me actually take 2A theory on a Calabi-Yau. So then you go to 6 dimensions, to 4 dimensions, because the Calabi-Yau is 6-dimensional, and we put here D4 and D0 branes. This you can lift to M theory, and then you have M theory on a Calabi-Yau times a circle, and then you have M5 branes, which are reduced on the circle, and they give you the D4 branes, and then you can have momentum along the S1, and that would give you the D0 branes. For both of these cases, we know quite well how to count the number of states. By the way, I mean, last time I didn't get to explaining Cardy's formula, but who of you are not familiar with Cardy formula? Cardy's formula for counting states? All right, then I'll have to spend a little time on that. Well, I'll do that at the moment when I get there. Yeah, let me think. So how do we describe these systems? The D1, D5 system and a D0, D4 system are very similar. They're actually just related by some T-duality along a circle. So what I will do is actually think about more of the D4, zero language. First of all, D0 branes what we think about are point-like objects, and they have coordinates just like point particles have. But if you have n d0 branes, then they are described by some matrix quantum mechanics. So instead of having just the usual x dot squared, so I have coordinates xi, and in string theory we generally have only the transversal coordinates. You can think about just as a point particle action. Actually, d-branes generally have a Born-Infeld action. I'm not going to write down the nonlinear form of that. I'm going to assume that I can just go to a usual quadratic Lagrangian. And then so I have coordinates xi, and then there will be interaction terms that look like that. And then there can be fermionic terms, and I'll call them just lambda. I'm not going to be, so this xi can be dotted with a gamma matrix, and then there's a kinetic term also for the lambdas. Now what is important here is that what I'm describing here is you can think about as the low energy description of the open strings that stretch between the d0 branes. So d0 branes are n of them, and then these are matrices which are like n by n. So this is an n-dimensional matrix. And then the strings that stretch between different d-branes are describing the off-diagonal modes. Well, what's on the diagonal, you can think about as associated to the strings that go to the same d-brane, and they are describing the coordinates of the individual d0 branes. And now this is not the language in which we describe the system of d4 and d0 branes, and the reason is that here we're going to look at the bound state of d4 with d0, and that requires a different kind of strings, because then you have to think about the d4 and the d0s together, and you get strings that go between. So the d4 is some extended brane, and then you can have strings that go between the d0 and the d4 brane. And it turns out that this is the degrees of freedom that are relevant for describing the bound states that I have between d0s and d4. So this is an n by n matrix because I had n d0 branes. Let me put sort of k. So I'm going to have an n and a k, k being the number of d4 branes and n being the number of d0 branes. So if you then ask what are the labels that I should put on the degrees of freedom going from the d0s to the d4, it's actually a label which has on one side n possibilities, namely where maybe I should call it alpha or something like that. And I have possibilities here, call it capital A, which runs from 1 to k, and this number goes from 1 to n. So then you have fields which are, you have again quantum mechanics, but the quantum mechanics describes a different type of fields. Here I would call them A alpha A. One way to think about the matrix, it's also a matrix, but it's not a square matrix. One way to think about the Lagrangian that I'm going to write down for it is by thinking about it again in gauge theory in higher dimensions and then sort of reduced. This is like indeed also a Yang-Mills theory, which I have reduced to the world line of the d0 brane. Here you have a theory which, in terms of superfields is called a hypermultiplet. And this is going to describe what I'll call indeed the Higgs branch in a minute. And what is called the Coulomb branch will eventually be constructed out of these fields, of these variables. The big distinction between this language is that here, as I said, I can take the eigenvalues. The eigenvalues are important when you impose the fact that these coordinates vanish of commute, I should say, the commutator vanishes, which is the case when we look at low energy. If we have a potential of this form, then if the coordinates commute, we can only describe them in terms of their eigenvalues. And here you have the D0 branes move freely in space. But in this language, we're going to have different variables, and actually this is a different branch. And the reason is that there's going to be couplings between these variables and the variables on the Higgs branch. So there's not just bosonic fields, there are also fermionic fields on the Higgs branch, which are called psi. The description I'm going to give is actually, I mean, this is, as I said, describing things like D0 and D4 branes. D4 brane itself also has a world volume action. It's again a gauge theory, and in that case it's a four-dimensional gauge theory, and it has a very similar action except that you have to write down now the usual f squared terms, etc. Now the bound states of D0 and D4 branes, the bound states, they're actually related to n instantons in a UK theory. Well, this is not writing very well. But so the UK would be the gauge theory on the n D4 branes. But the way to describe this n instanton configurations, you have a moduli space, is precisely in variables of this kind. So how do I now think about, well, so what is the analog with the language here? As already said, I mean, this is going to be the variables which I call then h, alpha a, and the x's on here are really the variables which we can associate with these eigenvalues. And the number n and c that I indicate, n is certainly going to be related to this number n. C has a, well, in this case, it's going to be related to k, but it has a more general definition, which I'm going to explain also in the situation when we are in M theory.
So you're going to consider k much bigger than n?
The central charge generally is indeed much bigger than n. And which, by the way, in terms of the Cardi formula, is not a very good limit. Except that we know that the conformal field theories we're dealing with here are not of the general kind. They're actually quite special. So I didn't say yet where the conformal field theory is sitting. Actually, it's in this language, and in this language where it's most easily seen where there is a conformal field theory. Because what you do is basically eventually concentrate on the S1, because the D1 in this language is going to be wrapping this S1, and D5 the entire space. Here we have a similar situation. Here we're going to take the N5 wrapping a certain force cycle in, well, maybe I should call this N also being the momentum. A certain force cycle in the Calabi-Yau, and then you can still wrap the S1. And eventually we're going to look at the dynamics along the S1, and there you can count the number of states. But in order to describe the space on which this is living, so okay, I should maybe make the picture of it. So you think about the Calabi-Yau, or you can also think about this K3 situation, but okay, it's quite similar. You have a force cycle in the Calabi-Yau, and actually this is where usually the letter P is used. So the 5 brane is wrapping this force cycle, but I also have a circle, an S1. Now, the way we generally think about this is that this is kind of small, and we're going to look at eventually what's happening on the circle. So we have this momentum going along here, momentum with quantum number n. And then we want to think about the effective theory that's living on this S1, which is a 1 + 1 dimensional theory. And that actually can be made into a CFT, a conformal field theory, which has a target space. Generally, conformal field theories have target spaces, and they are described by indeed the ways that this force cycle, the 5-brane, can sort of wrap this force cycle. So the equations that I'm going to write down here actually are going to indeed describe precisely the kind of target space that this conformal field theory is going to live in. And I'm going to do it actually in a particular case where I know how to write the equations, which is not the situation which is most relevant, namely where this is a compact space. I mean, for the situation here, it would also be a compact space. You're actually wrapping a K3. So that's a very similar picture, except that we don't have the entire Calabi-Yau. We simply have the 5-brane wrapping the K3 times the circle. But you can actually write the equations more easily when we are thinking about a D0, D4 system, where the D4 is basically infinite. I mean, just on an R4. Because there we have a good description of what are the n instantons in the UK theory, because there's a construction called the ADHM construction, which you can formulate in these kind of variables. So what I eventually want to learn from this is that there's going to be a big phase space described in terms of these variables, but I'm going to derive from it a smaller one, which is the one in here. So there's for this I'm going to use actually a paper that Edd Witten wrote around, well, 97, I think. He talked about precisely the conformal field theory on the Higgs branch, and he did it as follows. He argued the following. He said, I can use these variables. So something still remembers the fact that there is this n D0 branes, and I have the K D4 branes, is the fact that there's a UN acting on this space. So these variables, there's some generators. So quite generally, I'm actually going to leave out now the indices. I'm going to think about the variables H, and actually they're complex fields of complex variables. And they're going to have generators acting on them, which generate a UN group. So these TAs are generators. Of UN. And then you actually impose conditions that these generators vanish, and you also mod out the UN symmetry that acts on them. That gives you a space which is basically going to be the moduli space on which this conformal field theory is living. And
why is that the moduli?
Yeah, I'll let me explain that. So the full Lagrangian which you get from the D-branes is much bigger. Namely, it's a Lagrangian for these variables. And for they are also coupled to the variables that describe the Coulomb branch. But if you flow to the CFT limit, you actually will find that these things totally disappear from the Lagrangian, and you basically are left with a theory that imposes these conditions. Let me make this more concrete then. I'm going to write down the full Lagrangian then of this system, at least schematically. So it's going to be a 1 + 1 dimensional Lagrangian. There's going to be kinetic terms for the H fields, and there's going to be a gauge field that's coupling to the UN symmetry on it. Then there is the fermions. They sort of have a similar Dirac type Lagrangian. Then there's a coupling to these variables, which I call x squared. actually they're multiplying, now should I, how's this again? Yeah. So X are actually matrices in their n by n matrices. You can think about them actually as acting therefore on these fields. These are actually in the fundamental representation, or, well, how should I say this? No, it's actually, there's a more general way of thinking about it. Yeah, you can actually think about the xi fields also as just things that I can express in terms of generators. And so I can act with x on, yeah, I think I'm gonna do it like that actually. There's a coupling of x to h squared. Then there's also something similar where you couple x to, well, maybe I should, yeah, right. X also can act on psi. And then there is a term which is a d term, a field which is basically multiplying these generators. And finally, there's also a term that involves a fermion. So actually, here I have fermions in this language. They also couple to an expression of this sort, something like that, and there's a complex conjugate. Now, if I only keep these terms, you'll notice that there are no kinetic terms yet for the fields that I wrote down here. And they're basically Lagrange multipliers. This is a Lagrange multiplier for a constraint. This is also a Lagrange multiplier precisely for this constraint. And I can also integrate out the x variable. And then you'll find actually this is that x can be expressed. And now I'm going to just write it schematically in terms, well, there's just an x squared times h squared term here. And x is basically expressed in terms of the variables on what I call the Higgs branch. This tells us that we can think about this Lagrangian indeed only in those variables. But now I'm going to include, let me now include actually, this gauge field does not have a kinetic term yet. That's right, and so it's also going to tell me that the generators vanish, and it's also going to imply that I gauge the UN symmetry. But there are possible kinetic terms that I can write down. This, by the way, is indeed a conformal field theory if I associate the usual dimensions to these fields, namely they're just scalars. And this is a one form. But now I want to write down a kinetic term. Suppose I would write down kinetic terms for this. Then it would be indeed the kind of kinetic terms that I had on the board there. There will be a lambda d slash lambda. And there may be a d squared term. Yes?
Where the 1 plus 1 dimension of the single model?
Where it is?
There is d0 are 0 plus 1.
So, okay, so I made a jump here. I mean, I said already that there is a similarity between the d0, d1, d5, and the d0, d4. So if I think about this as a description of d0, d4, what I'm doing actually, I'm adding indeed an S1 and thinking about the theory that lives on the space of solutions of this Lagrangian.
So there is an S1.
So I now do the language, actually it's easier to think about it in the CFT language, what I'm going to say, because what I'm going to tell you now is that I can start from this Higgs branch and induce all the dynamics on the Coulomb branch simply by integrating out the variables. That's the main point of that paper, is that, namely, these terms are all higher dimension. So in the conformal field theory limit, you would not even see them, and you would totally end up on this Lagrangian. And if I so forget about this, then I'm indeed ending up just at the space of solutions of this modulo the gauge transformations, plus the fermions. So the dynamics here, this is really an example where the dynamics on the Coulomb branch is totally induced by integrating out the Higgs branch. yeah, I could have written down more equations, which I'm probably not going to do, but of course what I'm going to do is actually go to the language which is used on this side, which is sort of similar.
So you're starting integrating out fast degrees of freedom.
That's correct.
So the ultraviolet theory is what you call the Higgs branch.
That's correct.
And you're integrating out this conformal field theory, the ultraviolet, to get a non-conformal field theory in the infrared.
Yeah, but you can flow down.
No, I understand. But
You can even flow down from here, and then you change the central charge, and you get indeed a theory which is much smaller in terms of its number of degrees of freedom, but eventually just has its own dynamics. But you know that eventually it was originally derived from the bigger phase space. And I think the Coulomb branch, therefore, should really be thought of as being embedded into the Higgs branch, because, as I told you, actually all of the variables that I have.
so is this discussion predicated then on the kind of feeling that in the ultraviolet limit, the largest possible phase space is conformal?
No, it's not, of course. In the beginning of my lecture, the first lecture, I told you conformal field theories are just limits of something else. And I don't think the world is described by conformal
In
field.
this case, you're starting with that.
No, it's the corner where we know how to do calculations. Because I do think that there's actually something underlying even that conformal field theory. I'm not going to tell you what it is, because I don't really know what that is. But there is some way in which.
In this explicit example, that's a.
So, and this is an example where I can find a layer below the level in which we would normally describe our space-time, namely, which is, it is a conformal field theory, but it's expressed in terms of these quantities, which are more like the bifundamentals. And there may even be other layers you never know. But at least we have here a language where we can start from a situation which doesn't have a space-time, because this is entirely in internal dimensions. So the extra dimensions that I've added here in our description, to me, are just necessary to describe a Hilbert space from which I'm going to derive the positions that are going to describe positions in space-time. And as this makes quite explicit, actually this comes from a paper that Herman, my brother, and Micha Berkus wrote. They sort of indeed emphasize the point that the Coulomb branch can be thought of as being part of the Higgs branch, and that the coordinates that we see normally arise to say the zero branes can be thought of as being composites out of the variables on the Higgs branch. For me, this is just an example of how these things work, but I'm going to make it a little more general by indeed discussing the case for M theory, which is first again going back to this situation with D0 and D4s. Because what I will indeed argue now is that we can indeed start from a Hilbert space or a phase space which is formulated in this language, but you can also have, oh yeah, maybe I should have told you before. There's this term actually, and that's a very important term in the entire Lagrangian, because it will determine on which branch one is actually formulating the theory. If you, in order to be able to write something like this, or if it just looking at this term, if I just keep it in a Lagrangian, it tells you that when the Higgs branch is actually, as I said, parameterized by the fields H. So it actually involves things where the expectation value of H is non-zero. And that means you induce a potential for your variables X. And this is actually where why we are looking at the bound state. Because if your position variables are being stuck to a certain point, and that's actually precisely what's happening here, they will, if this is non-zero, the D-branes are drawn towards the D4 brane and actually are stuck on it. So this position, this distance, is measured in terms of the parameters X, but they can only acquire expectation values when H is non-zero, of H is 0. But then we also have to include the dynamics of these variables x. And then you have indeed these terms. So the Coulomb branch is described by, as I said, the xi's being non-zero, or at least maybe I should say it differently. Yeah, well, I think this is fine. That means I'm indeed moving the d0 branes away. But here I've also imposed the condition that these xi's commute by putting this potential to 0. Now, this is then called the Coulomb branch. Now, you might say, I'm either on this branch or on that branch, but that's generally not true, because these fields, there are many components. And in principle, I could have part of the components non-vanishing and part of components vanishing and have these kind of variables. And that would be a mixed Coulomb-Higgs branch. And this is going to be important for what I'm going to say later on, because the fact that we have a Higgs branch, a Coulomb branch, and something that may be in the middle is going to be, well, telling us that there may be different things to look at. Because one other thing that is going to be relevant is to think about the possibility where this is non-zero. And this is precisely what actually was discussed in the context of M-theory on this Calabi-Yau, or in the D4, D0 language, in a set of papers by Andy Strominger, David Gaiotto, and some collaborators. They looked at this Higgs branch, Coulomb branch transition in a slightly different way. So, yes?
So the point is that you can start from the Higgs branch, integrating it with the field and get the Coulomb, but you cannot do the opposite.
You cannot do the opposite, but one thing, so it's very clear that the Coulomb branch has a much smaller phase space than the Higgs branch. If you want to understand the entire phase space, you cannot do it from the point of view of just the Coulomb branch. But there is a way you can understand it if you allow yourself well, a little bit of imagination, which I'm going to tell about now. I mean, this is a particular situation where I take 2A theory on this. So I'm going to construct a supersymmetric black hole, and actually that's a situation that Strominger and collaborators looked at precisely constructed in this way. And then you look at the near horizon geometry, and there you can indeed go to a decoupling limit which looks like an ADS space. It's ADS2 times S2. And they think about the quantum mechanics of the D0 branes. So it's a system with D0 branes and D4 branes, but these D0 branes are again just written by some matrix quantum mechanics. And now there's a phenomena that, so they want to actually explain the size of the Hilbert space. Now, there was originally a paper by Maldacena, Strominger, and Witten that also already did the counting, and they did it as follows. They look indeed at the possible ways in which this force cycle can wrap something in the Calabi-Yau. I'm not going to enter in too much of the mathematics, but this force cycle, the Calabi-Yau has a certain number of force cycles, which we can label with a number A. So this defines some charges in the four-dimensional theory called PA, where A is the number of force cycles that you can have. Now, force cycles can intersect, actually 3 of them. You need, if you're a 6-dimensional space, you can intersect 3 of them. And they define something which is called the dimension of the space of possible embeddings. And that dimension is what's going to be the analog of my number C. It's going to be a cubic expression where this counts the number of intersections, self-intersections of this force cycle. Well, I haven't drawn it in a way that it can self-intersect, but if you go imagine how force cycles are embedded in a 6-dimensional space, they can actually intersect on a 2-cycle, then they can intersect again, and then intersect in points. So you have a triple intersection number for the number of 4 cycles. Anyhow, this defines the dimension of the possible moduli of this embedding. And then they argued indeed that it's a CFT with this as its central charge. And then I had the circle which had a certain momentum around it. And I'll actually describe later on how you count then the number of states, because that's a combination of the numbers C and N. But there's a different picture of this which I was about to explain here. Namely, I'm going to think about this from the point of view of the D0 branes. So the D0 branes are described by these matrices. And generally, you would like the off-diagonal modes to commute in such a way that you can identify the individual D0 branes. But there's a phenomenon called the Myers effect, which is when you allow actually the off-diagonal modes to be non-commuting, or actually these matrices to be non-commuting. So if I have D0 branes and I have 2 coordinates, say call them X and Y, and they don't commute, that actually means that you can write them as matrices, a matrix identity where this is some matrix where you impose, well, for instance, that it's up to some unitary conjugation, something proportional to the identity matrix. This actually describes an D2 brane in the XY plane. But this is just, well, a particular case. I mean, here we have an S2, which is also a 2-dimensional space. And they argue that it's possible by having non-commutative coordinates to turn the D0 branes into D2 branes that wrap the D4. Sorry, the S2. Why do they want to get to the D4 branes, D2 branes? The D2 branes, namely, are the magnetic duals. There's a duality between branes. I mean, if a brane has a certain charge, there's a dual charge, the magnetic charge, and the rule is basically that the dimensionality of the brane to get its magnetic dual must be together, it's dimension 6. One way to understand this is that this is actually coupling to a 3-form field with a 4-form field strength. And if you dualize this, you get something that has a 6-form field strength, which couples to a C field, which is 5 components, and therefore it couples to the D4 brane. Now, this charge which I had here is actually indeed associated to a 4-form field strength. And it also, yes, how should I say this? Well, I'm going to cut this short in the following way. This D2 brane actually is going to be thought of as wrapping indeed an S2, but it's going to move also as a, yeah, so it's 2-dimensional. If it wraps the S2, it's really wrapped here, but the entire space-time looks like AdS2 times S2 times the Calabi-Yau. So this D2 brane is actually moving also in the Calabi-Yau, but in the background of the D4 brane. And if you then look at its Hamiltonian, its quantum mechanics, you can actually calculate how many states it has, how big the Hilbert space is. You find that the Hilbert space of the D2 brane is actually precisely this dimension. So there's actually a dimension of a Hilbert space. This central charge actually labels the dimension of some Hilbert space. But there's n D0 branes which turn into a D2 brane. And then it turns out that the charge, so the n of the D0 branes can distribute itself over the D4 brane in such a way that you can have for each of these D2 branes a Hilbert space of this size. There's a certain combinatorics that then counts the dimensionality of the Hilbert space, and that will be expressed in terms of the C, numbers C and N. So now I'm going to tell you how to do that counting, because that's basically the same as the Cardi formula, which we have where this is the central charge and this is then the number of excitations. So now I'm going to briefly explain how to think about the dimensionality of the Hilbert space from the Cardi formula.
You will do the calculation in the gravity side, right?
No. We know, of course, the gravity side here in this case. So on the gravity sides, we want to reproduce the entropy of the black hole that's being described here. So well, let me first give you the formula, then we can discuss what it looks like. The entropy is going to be equal to, so if, yeah, usually we write the central, yeah, I'm thinking about indeed a central charge, which is, let me write in the usual form where the central charge is just a small letter c, and then it's 6 over 6, c over 6, and then there's L naught minus c over 24. This is the usual Cardi formula. So L naught for me is going to be playing the role of n. And small c, well, I wrote it actually as capital C for some reason, but anyhow, it's not that important because I didn't really want to fix all the normalizations here. So let me explain where this formula comes from. So this is the entropy in a CFT with central charge C at level sort of L naught. So how do you count that? A CFT has a partition function and the partition function can be written as a function of a variable tau. Tau is actually going to be also expressed in terms of another number which are called q, and then you just write down a series q to d, and now I'll write it in terms of L naught. Or maybe I'll write actually I'm going to write it actually as a function of n. So L naught, as I said, is I'm going to write it in terms of n, and then I have some degeneracy d of n, and for the partition function to have a nice properties under modular transformation, actually we require to have here the c minus c over 24. Now I want to know this entropy, and this entropy is going to be equal to the logarithm of this number dn, where again I made these identifications. So how you can calculate this is by doing a contour integral of the partition function where I subtract, and let me actually now write it indeed in terms of the tau, and then I write the partition function z of tau. Now the way you can derive Cardi's formula is by making use of the fact that this partition function is modular invariant. Which means that z minus 1 over tau is equal to z of tau. This actually has to do with how the torus sort of has a symmetry between exchanging its A and B cycle. Well, I'm just going to put this in here because it turns out that in doing this integral, we're interested in a particular limit of where tau is going to be, namely in the case when n is very large, we can expand this, and then we know that we have to be actually at values for tau very small. But then I'm going to use this transformation to make tau to minus 1 over tau, and then this 1 over tau becomes very large. And then from this expansion, maybe I should put in the 2 pi I tau. From this expansion, you'll actually see that it's only the term that's minus c over 24 that's going to be dominant. So I'm going to replace this by, or actually this expression, yeah, let me actually put it in this box, by something that looks like e to the minus, well, there's a minus sign here. I'm going to replace this by minus 1 over tau, so it's plus 2 pi I c over 24 times tau. Now, in doing this integral, you're actually going to use a saddle point approximation, which means I can differentiate. So I'm multiplying this with this factor, and that means I can differentiate with respect to tau to get the saddle point. So a saddle point approximation gives you an equation for tau. If I differentiate this, I get tau squared equals n minus c over 24 over c over 24 with a minus sign. So I can also write it like this. Tau is going to be I times the square root of this expression. And now if I let me make this a little more readable by taking this one out. So I'm multiplying these two exponents, and I'm putting in the value, this value, and then you will see that the two exponents basically become the same, and they add up to something that grows like e to the 2 pi. Because of the 2 pi's, the i's drop out, and then I get indeed something, well, if you work it out, precisely the c over 24 minus c. Well, actually, maybe I should even make it clear how it comes about. This makes it easier. There's a 4 pi because the 2 pi's actually add up. And if I insert this expression, I think I did it the other way around. Yeah, I did it wrong, sorry. This is 1 over tau. Yeah, so if I put that in here, you'll see that this multiplied with c over 24 gives you exactly this expression. And the same thing here, if I put it in here, you get the same expression. And this is giving you the Cardi formula. Anyhow, this is a quick derivation of what the formula looks like. But this is also what we know now. Here is the entropy. It's known from the gravity calculation that this system with n d zeros and these number of d4s has precisely this entropy, where n, as I said, is the number of these zeros, and c is precisely this number p cubed, which I have in there. So why was this relevant for the entire discussion? I'm going to actually be interested indeed in the yeah, I should say, make a jump back to the situation. Yeah, so I'm going to borrow this at least for my more general story. Any questions about what I, yes?
So I'm a little confused. In the field theory side, you have some flow from a theory of the Higgs branch
Yes.
to a theory on the Coulomb branch.
Yes.
Now the theory on the Coulomb branch is the CFT in the IR, right?
Yes.
And in the Higgs branch is not a CFT.
It is actually. The Higgs branch starts from a CFT.
But if the expectation value is non-zero?
What we no, actually, in order to have a expectation value which is non-zero, I need the field from the Higgs branch to be scalars. I mean, they should not have any conformal dimensions. Then you can have a conformal field theory where you associate an expectation value to that, and that would be sort of the. So it's a target space.
It would break the conformal variant spontaneously and trigger the algebra flow?
I'm not going to. I'm thinking here about the full phase space in terms of the Higgs branch, and so what I've calculated here is the central charge. This is the central charge of the theory on the Higgs branch, and this is the volume of the phase space on the Higgs branch, which I've calculated here.
So this calculation is for the
So, okay, we have a microscopic, so, okay, let me just summarize and then it will be clear. So we have a Higgs branch, because this is the general thing I want to keep, which, as I said, is characterized by two numbers, a C and an N. And in the particular case that I looked at, it is described by a conformal field theory, and then we can calculate the volume of its phase space, or the number of states, and that is characterized by the Cardi formula in, well, whatever, I mean, actually, let me just schematically write it like this. It's something like the square root of C times N, and, well, yeah, this is just a schematic expression. Now, I want to think about the Coulomb branch, and the transition to the Coulomb branch goes to the variables x, I, which are n by n matrices. And actually, in the Coulomb branch, I also want these matrices to commute. So then I can eventually go to the eigenvalues. But they are derived from the variables which I had here, which were my variables h and psi. So I start from a big phase space in terms of these variables. Its central charge, I told you what it is. It has two numbers that characterize it. C being the number of degrees of freedom, and N being the number of excitations. But then when I go to the Coulomb branch, the only number that I basically see is this number N. And the size of the matrices is determined by it. And when I impose that they commute, I get this number of eigenvalues. There is a story back, namely, if I think about these variables on the Coulomb branch as indeed D0 branes, I can go to the phase where they don't commute anymore. Then they start being more aware of what is in the Higgs branch. So if I want to go from the Coulomb branch back into the Higgs branch, I have to go through this phase in terms of what I would call the D2 branes. So the story that yes? Yes.
C is supposed to be much larger than that.
Yes, that's good. This derivation didn't work for that.
So
You know the story. The story is that, okay, I have to tell this a little. All right, so there's, this is the derivation from the CFT side. There's another derivation of the same expression, which is when I think about this Hilbert space of one D2 brane in the background of this D4 branes. Its dimension was equal to C. But if I have the way I define my D0 branes, I have to couple them to the D2 branes, and they generate what's called a symmetric product. So the Hilbert space is actually a much bigger Hilbert space where I have to count all the ways in which this capital number N can be distributed in partitions of N. And if you count the number of states on this one, it's some dimension of this Hilbert space. Well, you have to define it in some supersymmetric form. This actually has exactly the number of states which goes like that. And it's the fact that there is this symmetric product that allows you to do things like what's called a long string phenomenon. And then you're basically going from a situation which has a high central charge because of the long string phenomena to something which has small central charge but much higher excitation. So the growth of this state, of this Hilbert space, even when the dimension of the Hilbert space, which I call C, is larger than N, you can still trust this expression basically because I go to a long string picture. So there's a way of deriving this expression in a symmetric product fashion, and then you can still use the Cardi formula, but then you should actually not think about this central charge as being the central charge, this one, but as of a very long string. And then you sort of bring down the central charge, but you raise the number n in such a way that the product is constant. So we know that this formula, even though we go to a regime where the Cardi formula doesn't hold, because of the combinatorics of the whole situation, it still applies. Yes?
I want to understand the relation between the geometry and the safety. Can you think about the geometry as, the black hole is a D0 brane?
It's a bound state of D4 branes and D0 branes.
But can you think about the geometry as describing this D4, D0 system dual, but in the near horizon of the D4 brane? How do you get the ADS to?
Oh, that's the near horizon limit of, so what you're doing actually is you're thinking about the near horizon limit of the D4, D0 system. But then we describe it in terms of the quantum mechanics of the D0 branes.
But the singularity is a D0 type singularity.
There's no singularity if you go to the near horizon limit, because there's just an ADS2, because you sort of decoupled the whole thing. But this is not, I mean, anyhow, I'm not going to think about just black holes. I want to sort of generalize this description to situations where I don't have black holes even. So, because this is why I'm describing it sort of in this general language. I want to have a big phase space, not described by very detailed numbers, except the two numbers which I have here. The size of some Hilbert space of, say, a single particle, a single excitation, but then I have an n number of excitations, and then I get a Hilbert space which is sort of roughly of this size. Now, there is a way to go from the Higgs branch to the Coulomb branch, which is described in terms of these matrices, and eventually the degrees of freedom that we associate with particles in space-time are the things that are described in terms of the eigenvalues. But if you think about how forces arise, you have to really think about what I did in all these steps in integrating out these degrees of freedom. And for instance, the gravity among these eigenvalues is induced by integrating out these off-diagonal modes. And this is basically the calculation I showed the other day, is namely, it's by integrating out the strings that stretch between two D0 branes. That gives you the closed string exchange. And indeed, you can show it that integrating out off-diagonal modes generates the gravity among these eigenvalues. But there's a step before that, which is indeed represented in this bigger phase space, which is the Higgs branch. Yeah, let me actually tell you, yeah, this is how many minutes? I have 20 about? 30? Okay, all right. So let me now go back to gravity, actually. The language of these zero branes and open strings and closed strings, it has to do with perturbative string theory. I'm going to be interested to eventually apply it to a non-perturbative situation, and then we think more about M theory. Now, there is not a lot known about M theory, although there is some suggestions were made about how to describe it. Namely, you can think about these zero branes we have in 2A theory as being indeed 11-dimensional gravitons which have a certain momentum. So if you take M theory on S1, this is equal to 2A theory. And then the D zeros, so here I have a graviton with momentum n over R. That corresponds to n D0 branes. This idea was used by Banks, Fischler, Susskind, and now I forget, Schenker, to describe a matrix. They sort of thought about M theory as a theory of matrices, matrix coordinates, and exactly with the Lagrangians that I wrote down before. Plus the fermionic terms. One motivation for that is also that indeed membranes which we have in M theory can be thought of precisely by taking these configurations of matrices and allowing these matrices not to commute. Because then if you have these non-commuting part matrices that describe membranes in the M theory language. Eventually, of course, you want to go down to a 4-dimensional theory, and this compactifications well, it's a long story. I'm not going to describe the details of it. But it's not entirely, I was not entirely successful. And one of the reasons is that it turned out that this matrix theory didn't express all of the degrees of freedom that we expect M theory should have. One thing it didn't have, for instance, was part of the 5 branes that we would like to have in M theory. So M theory has membranes, 5 branes, and of course things like these gravitons. Precisely when you get down to 5 or to 4 dimensions, things started to break down. And I think the reason is that, indeed, if you want to understand M theory, you shouldn't start from matrices. And these matrices describe, in the very same language as I had here, points like objects, which are like the gravitons. But if you want to have the action for it look like this, you're already telling it what the space-time looks like. This is the space-time that we start from. It has its own dynamics in space-time. But if I want to understand gravity in some emergent way, I should also explain where the space-time itself comes from. So I really think that this matrix theory should be thought of as also arising in the same language as I did before, as after integrating out degrees of freedom, which I think are in the Higgs branch. So there should be a Higgs branch formulation of what M theory is in 4 dimensions. And then I induce all of the dynamics of these matrices by integrating out the variables on the Higgs branch.
Well, there are no dimensions here so far in the matrix theory.
Well, if I look at the single eigenvalue in here, it's moving on a space-time, which should, in this case, be Minkowski space. Why would it be Minkowski space? It also has inertia. I mean, it has a certain mass. And if I want to think about force as being in the way I want to have emergent forces, I should not write down inertia from the beginning. So the language of this, so the kinetic terms that I wrote down here should actually be obtained from integrating out the degrees of freedom on the Higgs branch, because then I'm going to explain what inertia is. So I'm going to start from a very abstract Hilbert space in which space-time indeed has not been defined yet, or at least space has not been defined yet. But I'm going to think about that Hilbert space precisely in the language that I had there. I have some set of fields. They don't even live in space-time, but they have a UN action. I can couple matrices to it, but then if I integrate out these variables, I'm going to generate an action that we know about already describes M theory. This
Are you saying you can write down something like, you can derive this from a Higgs branch? This is the Coulomb branch of Higgs.
This is
Of a theory with H's or something like that?
That's correct. And I'm going to actually deduce this from the way that gravity works.
But there will be an explicit matrix theory which describes the Higgs branch.
I'm going to give you my best guess. I'm going to use actually the language that was used for the D0, D4 brane. And I think I should go to the same steps that BFSS did.
Trying to go backwards, which, as you answered Cope, isn't possible.
What do you mean?
So you're guessing how to go backwards from the Coulomb branch to the Higgs branch.
No. So I'm saying I'm going to start on the Higgs branch of a D4, D0 system. But now I'm going to think about the D0 branes as being 11-dimensional momentum, and I'm going to go to an infinite momentum frame. And I'm going to construct something that looks like M theory, except I'm formulating it now in the variables that are on the Higgs branch. Because I know in that context that if I would integrate out the Higgs branch variables, I would induce the dynamics of the D0 branes along the lines that I described. So there's a way I can get the dynamics of the D0 branes by integrating out the degrees of freedom on the Higgs branch.
So this is, aside from the general picture, an equivalent formulation to M matrix theory.
No.
Not M theory.
No, it actually adds degrees of freedom.
It has degrees of freedom.
So it's a much bigger Hilbert space even than this language.
From which one can derive
The one we know about.
matrix theory.
That's correct. with its dynamics. So I'm indeed conjecturing there is a Higgs branch formulation of M theory in 4 dimensions, from which if I integrate out those variables, I'm going to induce what we know about M theory in terms of matrices. Sorry? You can try to do it in 11 dimensions, but I have a feeling that the Higgs branch, the reason why we needed the extra dimension is really to construct this bigger Hilbert space. And I think the fact that we want to construct things like 5 branes, things like that, I mean, I think I don't want to, in order to get gravity, I need really these Hilbert spaces to be finite dimensional, for instance. I want to have compact phase space. So I'm really thinking about more what would be a 4-dimensional description of what M theory is. So I'm conjecturing that there is a 4-dimensional formulation of M theory that should start on the Higgs branch, and where our 4-dimensional coordinates are derived along the lines that I described from the more abstract Hilbert space which we have in here. And the only thing I want to keep from this Hilbert space is these numbers C and N. And what I want to describe at the end actually is what are these numbers C and N? Yes? Yes.
Which includes the shifting X also. I mean, basically, you have to keep the central charge going to include the description of the theory, and you can realize it by linear bilateral on the axis.
I don't think that you're claiming there is a conformal field theory on the Coulomb branch that is equivalent, or?
You can compute the central charge of the Higgs branch also on the Coulomb branch, basically.
No. But if
you know it because you get the DLCQ of the 5 brane that has a linear dilaton.
Yeah, but linear dilaton, of course.
So, well, basically the point is that if you start with something like this, it's very difficult to get something that has translation symmetry in the axes. And if you want to find a similar statement in quantum mechanics, then I mean, there's a way of phrasing these axes geometrically as some axis on Coulomb branch. And then also it's difficult to see how you get translations on the axis.
This I understand, but then there may actually be a reason. Okay, but I will provide evidence for why such a picture might be correct. Actually, from the gravity side. And well, I'm gonna run a little bit short of time, but anyhow, let me. Sort of start now from the other end, because I know a lot about the gravity side. We know, for instance, that for black holes, we know very well how to calculate the entropy. It's A over 4G. There's a way of thinking about this, and actually there's a number of papers that have been written. It's best known in 2+1 dimensions. There people can calculate the entropy of a black hole using sort of conformal field theory language. And so you would like to be able to write this in the form of a Cardi formula. Sorry. This was done by indeed thinking about isometries on the background of a black hole. It's a series of papers by Brown and Hanaud, and they were followed by Strominger. Carleb has written on this, and what I'm going to tell you is just a summary of what these people have concluded. So L0 is one of the Virasoro generators, and also the central charge appears in it. So you want to think about the gravity theory on a background of a black hole. So black holes, we know we have horizons. And if I draw the picture in the usual way, this would be the Penrose diagram. Eventually, we know that there is a horizon, and people want to get the entropy from looking at the horizon in the neighborhood of this point where the future and the past horizon intersect. There's actually general formalism due to Wald that expresses the entropy actually as an integral over the horizon of a certain quantity, which is expressed in terms of conserved charges. So there's actually an expression where you think about this horizon, which indeed is an S2 of some quantity which is called usually Q tilde, which is some conserved charge in the geometry. But more generally, you can think about conserved charges associated with killing vectors or by any diffeomorphisms that you have. So let this be some diffeomorphism on the background of this black hole. Then there is a conserved charge associated to that. And from the gravity Lagrangian, people constructed now commutators of these, say, two of those. And in this way, you can generate an algebra. Now, the Virasoro algebra is a particular algebra where if I have I have a set of xi's labeled by an integer n. Basically, by doing a Fourier expansion in a certain set of angles, then you can write down the usual Virasoro charge form, which is algebra form, where this goes to psi q of psi n plus m, plus then a central charge term. And now I forgot the usual normalization, but there's something. There's some term like that you want to have. Now, you can do this indeed in the gravity theory, and then it turns out that there is a very canonical identification of what would be, so L0 would be the charge corresponding to the vector field which has n equals 0. So you have, so the LNs generally have, are these objects, but the L0 is the one with psi equals 0. Now, what people have identified indeed is what is the central charge, and also what is then the appropriate L0 value. And it turns out, and that's actually already clear from this expression, there's only one number here, namely the area over 4G. Here I have two numbers, L0 and C over 24. It turns out that we're going to be at a special value, namely where L0 is going to be equal to C over 12, C over 12, and this is going to be equal to A over 8 pi G. If you namely do this, you find that if I insert this in here with these expressions, S will indeed be, well, it's very quite easy to do. If I just insert here C over 12 and work out this, you'll find that this will be equal to 2 pi times C over 12 and therefore equal to A over 4G. So these are the identifications that people have made for black holes. But I would like to have a more general identification of what L0 is. And actually, I will make use of what people have done in matrix theory. Precisely the same authors actually that thought of this idea have looked at black holes and tried to explain this entropy using a matrix language. And then they found a different identification of what n is. And actually, it's going to be equal to this one in the case of black holes. So I'm going to actually identify L0. And actually, for 4 dimensions, it's a very easy expression. It's m times r. For a black hole, m times r is going to be equal to precisely A over 8 pi G. While this is going to be a more general identification. I'm going to actually explain this more in the coming lecture. And actually, I will provide, as I said, evidence for why this is a correct identification. So the two numbers which I had, the C and my N, will have a meaning in more general situations in terms of the geometry, either giving you the area or the mass in the system times R. So I already told you a little bit, I want to think about a phase space associated with a particular part of space-time, where I think about the space-time as having an area, a certain mass in it, and a certain linear dimension, which you can think about sort of as the average curvature radius of this geometry. And then these identifications turn out to work. So next lecture, I'm going to actually work this out more in detail and actually provide evidence why this is a correct identification, also from data, because this is where the connection with dark matter will be made. First, let me ask if there are questions.
So this is a conjecture?
This is going to be a conjecture. It's a proposal for what I'm going to do. And actually, as I said, I will provide more evidence for that in the next lecture.
Conjecture relating to piece of space-time
With
geometrical size and energy to some underlying microscopic theory, which if you integrate out the vast degrees of freedom.
Yeah. So what I will need conjecture is that if I want to think about describing this part of the space in terms of a microscopic description, I'm claiming there is a Higgs branch description of it, which has these identifications. So if I want to think about, for instance, counting the states, I would do it sort of in a similar way as this. If I want to think about how the degrees of freedom in that space emerge from the underlying dynamics, the number of degrees of freedom will be counted by this number. And the geometry eventually is captured, of course, in terms of the area and the curvature radius. But one thing I can do, for instance, is really calculate now the reaction forces on this geometry using the principles of the previous section. Of the lecture. There it's unique, and actually the reason there is that we're in a thermodynamic situation. More generally, we are in this, what I call the Born-Oppenheimer situation, where you can still think about fast variables that you've integrated out, but they don't give you a thermal heat bath, they give you something more like a fast dynamical system that has been integrated out.
But, so the idea is you imagine starting with a black hole.
If you want to argue, sorry, yes, okay.
And then if you want guessing of the microscopic system, which would also apply to more complicated situations.
Well, maybe I should say it indeed like this. Suppose I would start from a black hole. A black hole for me is really in the Higgs branch. We don't see any matter there. But I know that the black hole radiates. And what I can do is try to get the particles out of there and bring them into space. That is like pulling the particles from the Higgs branch into the Coulomb branch. And you're going to have a mixed states when you have still the black hole and the particles in the Coulomb branch. But you start from a very big phase space. And now suppose I would take all of the particles here out and I want to represent them as something like this. The size of the phase space has not changed. But the Coulomb branch description is much smaller. So there's actually a much bigger phase space associated to this dynamics. And this is partly what will be responsible for the forces that we see. And you can let it collapse again. And then what you'll see, it will collapse back into the black hole. But in general, I'm claiming there is a part of the phase space which is still in the Higgs branch. There's part on the phase space which is in the Coulomb branch, and actually this is where the particles will live. But there's also stuff in between. That's dark matter. This is dark energy, this is matter, and the stuff in between is dark matter. And that has, the way to describe it is by allowing indeed matrices to be non-commuting. That's the in-between phase, because if you want to go from the Coulomb branch to the Higgs branch, you have to go through this non-commutative phase, otherwise you don't enter the Higgs branch. And so gravitational collapse is the direction that goes this way, The emergence of matter and space-time is in the other direction. And if you believe that the matter we see has emerged from the Higgs branch, you actually understand why there would be something left over in the in-between sector. And you can actually calculate how much it is. And this I will do next time. Actually, from these numbers, I can actually get the calculation, and I can sort of even match it to the data. I think I'm sort of done. Yes.
So you said that you have some guess about the Higgs branch of this M theory, and you can get this rotational properties that you know. What about other properties of M theory that you know, kinds of dualities? Everything that is known about M theory you can construct from this.
What I can construct, I mean, what I have here is the membranes I have. The membranes I can make. I can make the fibranes I need as well. I mean, otherwise I can't construct this Hilbert space that I have. I mean, the degrees of freedom that formulate the Higgs branch are actually the ones associated with fibranes. But I think most of the symmetries that we have in M theory is because we're like to go every time to a special limit, like the conformal field theory. We go through an RG flow where you fix your beta functions, and then suddenly magical symmetries will appear. But this is an emergent symmetry that comes about. I mean, quantum field theory does not have a Virasoro algebra, but once you go to a fixed point of it, it may get it. So I think a lot of the symmetries that we see in string theory are emergent symmetries because we have gone to a fixed point of a certain renormalization group. So I don't think that nature is described by M theory, but it has very similar principles as the one we've discovered there. So this is why I want to focus on principles, because I don't think that we have a very good guess of what really the fundamental description of nature is, but we can describe its fundamental, the basic principles. So I'm using the principles that we sort of extract from M theory and try to apply it to what we may see in nature.
No, but there is a mathematical, I think Kobe was asking the same question I was asking. Is there just mathematically a lesser goal?
Is there an example?
Branch formulation of matrix event theory.
I think there is, but I think it's not that easy. And this may be partly because we're not able to describe de Sitter space in string theory, and because we have not really understood very well how to go to a mixed Higgs Coulomb branch. And I also think that part of the energy of the system is still on the Higgs branch. And so we're not entirely on the Coulomb branch, we're not entirely on the Higgs branch. This is a complicated state. And this is where all of the dynamics comes from. And I think if you allow indeed part of the energy to be on the Higgs branch, you understand what dark energy is. And you have to describe it in terms of de Sitter space. So I think we have to go to a situation where we, inside the Higgs branch, embed our Coulomb branch in there and allow part of the dynamics still to take place there. Yes?
So the existence of these various branches is really contingent, at least in anything we understand, contingent on supersymmetry. Do you have some thoughts on, probably when you want to describe, for example, your dark matter, or you ultimately don't want, or maybe you do?
I think the supersymmetry is needed in controlling our calculations of these extra dimensional objects. Because if you want to indeed see how the flat direction, I mean, I did the calculation yesterday, you want to have these cancellations happening, otherwise you find that the linear potentials will grow instead of. So there is a certain amount of cancellations that are required. But this may be due to the fact that our only capability of describing this is by adding too many degrees of freedom, which we have to sort of cancel anyway. So I'm not totally sure, but I think the supersymmetry required here is not the one that we normally would associate with supersymmetry in space-time. It's something like, I want to have some degeneracy of states in the, or the...
So you think, for example, so this might not be realized, the supersymmetry of the microscopic theory you think might not be realized?
The supersymmetry which I wrote down in the beginning of these H and its size, they actually live in the extra dimensions. They don't have any, they don't need to be supersymmetry that is realized in space-time. So there's a certain way that the fermionic and bosonic oscillators that I sort of want to integrate out to get my gravity induced, they have to cancel in certain ways so that otherwise the potentials will not be flat enough. But whether this has any repercussions for what's happening in space-time is not entirely clear from the system. And I think the fact that we are not in the ground state, actually the calculation I did of this black hole entropy already tells me we're not in the ground state. That may already be sufficient to sort of break the supersymmetry in our system. I mean, the zeta space has already a problem with supersymmetry anyway. Yes?
Talking about lesser goals, and there was a program a while ago to start by using topological theories which don't mention gravity, like I think something your brother did, for example, for the black hole, what Edd did using the group SL2R and SL2C, using a Chern
okay.
and then trying to get gravity. Yes. So, does this somehow sit as a baby example in your case, or is totally orthogonal?
I think it's really, that must be totally emergent. And actually, one thing that I mean, okay. No, I think that's really something that comes after integrating out many steps that you can make that into an effective description. Also, the open string language, as I said, is for me something that I already want to introduce from a formulation without gravity. So gravity, I don't think that gravity or the dynamics of space-time is really what would be the microscopic description to start from. We have...
In those cases, it would just gauge theories. There was no gravity.
No, but that's just because you rewrite gauge theory as I mean, gravity as some gauge theory. Actually, one thing, I mean, the open string field theory is a Chern-Simons action, and I think for me that already is an indication that it's being induced by integrating out something else. And actually, those actions you're talking about have the same properties. So in a way, I think we shouldn't think about Chern-Simons actions as being sort of the fundamental language. We know they have to do with anomalies generally, but so I don't think that's not related to what I'm doing here. Okay, yes.
Maybe these questions were asked in different ways, but I want to sharpen things for me. String theory is already a theory where gravity is space-time.
So emerges, you say?
String theory, gravity in space-time emerges.
Yeah, but not in a very precise way yet.
I think it is in some precise way. And in all the examples that I saw here, I saw known examples in string theory for the last 15 years, which you reinterpret. Now we want to form a principle that includes all these examples, all of which are taken from string theory.
Yes.
Expect this principle to give something different for which string theory is an example, or it's going to be just reinterpretation of string theory with consequences?
I think, okay, one thing we would like to know, what is string theory? And I also want to think about eventually our formulation likes to start from principles instead of a guess of what the microscopic...
Do you expect it to be an answer to the question, what is string theory?
Yes, I already actually, if I would have finished my last lecture a little earlier, or I would have said, I mean, if I had a little more time, I would have told you what it is. It's a fixed point of a renormalization group in which we extend our G-flow by allowing coupling constants to become dynamical. This is not a procedure that has a fixed point from the beginning, but once you go to the fixed point, you find that this is where open-closed string dualities appear and where UVIR correspondences appear. So I think string theory is like conformal field theory, a particular limit of a much more general framework where you can get to a fixed point. And what I've been doing here is sort of extracting from what we know from string theory the general principles that I think that can be applied to nature. And I think I can draw conclusions which I would not have been able to draw if I would kept the language that we now use for string theory, which in a certain way has been using indeed supersymmetry and all kinds of things in very restrictive ways. If we want to apply string theory to nature, which hasn't been done for decades, I mean, then you have to be able to look at string theory in a little bit different way.